In this video, we're going to go over the concepts that we've covered in Unit 5. Let's start off by talking about solubility. Solubility describes how well a solute will describe in a solvent. And when we're talking about solvents, more often than not, we're talking about water. And water has been our focus for the majority of this unit. So why is water such a good solvent? Well, dissolving involves breaking something down into its pieces, whether it's an ionic compound and you're dissociating it into its ions, or it's a covalent compound and you're breaking it down into its molecules. Dissolving means to break apart and surround by water molecules. So something that's a good solvent will be able to break the bonds between the pieces and stay between these pieces so that they can't reform. What is the property that water has that makes it so good at this? Let's take a closer look at solubility and water's polarity with an example. Let's look at ionic sodium chloride. When an ionic compound dissolves, it dissociates or separates into its individual ions. We know that ions are charged particles. Now, water molecules don't have a charge, but they are polar covalent molecules, which means they have a more positive end and a more negative end, which gives them what we call partial charges. Now, if we look at a water molecule, we have an oxygen atom with its 6 valence electrons and 2 hydrogen atoms, each with 1 valence electron. Now, the oxygen is a much larger atom than the hydrogen, and it has a much stronger pull on these electrons. So when the water molecule forms, the electron for hydrogen gets pulled closer to the oxygen than to the hydrogen. So although this is a covalent molecule and the electrons are shared, they're definitely not shared evenly. The oxygen ends up taking more of that negative charge of the electron than the hydrogen does. That, along with the 2 unbonded electron pairs, gives the water molecule a partial negative charge on the oxygen end and a partial positive charge on the hydrogen end. So the molecule itself doesn't hold a charge, but there are poles, or oppositely charged ends of the molecule. And that's why we call the water molecule a polar molecule, because it has poles. And these poles influence how the water molecules interact with these charged ions in solution. The negative pole of the water is much more attracted to this positive sodium. So it's going to push this negative chloride out of the way so it can get close to this sodium. Now the negative chloride is actually much more attracted to this positive end. And what ends up happening is that the water molecule puts itself between the 2 ions, preventing them from reforming, keeping them dissolved or dissociated in solution. So the pull that this polar molecule has is enough to separate the ionic solution and keep it apart. 2 specific kinds of solutions we talked about this unit are acids and bases. And we looked into neutralization reactions where acids and bases are combined to make a salt and water, a neutral solution. So neutralization reactions take place in water or in solution, and they create water as a product. So one question we looked at was, why is the solubility of the acid and base important for neutralization? If the acid and base are soluble ionic compounds, it means a couple of different things. 1, the compound will dissociate into its ions in water, which then means 2, the ions are available to react. Let's look at an example of a neutralization reaction with two soluble ionic compounds. When we put something like hydrochloric acid and sodium hydroxide together in water, the first thing that's going to happen is they're going to dissociate into their ions. Those ions are charged particles, and the water molecules that are already present have partial charges because they're polar. The hydrogen ion is immediately going to go find a water molecule to hang out with to become hydronium. And then the other water molecules who still have their partial charges are going to work really hard to keep the positive sodium and negative chloride apart by getting in between them. These partial charges keep the sodium and chloride ions from reforming. Meanwhile, the hydronium and hydroxide realize that they'd be happier being a little more balanced or uncharged. We end up getting water as a product. So if the hydrochloric acid and sodium hydroxide weren't soluble, these ions would never be able to form together because they would be still stuck in their original form. So here we have the balanced chemical equation for this reaction. We have soluble base and a soluble acid combining to make a soluble salt and liquid water. Now if we separate this equation into its ions, we see something interesting. On the reactant side, we see all of these ions in solution, and in the product side, we can see where some ions combined and others just stayed floating in the solution. The ions that stay floating in the solution are known as spectator ions, because just like spectators at a sports game, they're not actually participating, they're just kind of hanging around and watching. If we remove the spectator ions from this equation, what we end up with is called the net ionic equation. So if we get rid of the sodium and the chloride, what we're left with are the ions that combine in a new state. So in this case, we have hydroxide and hydrogen combining to make liquid water. When we have these types of balanced chemical equations, we know that we can make predictions about how much product is made from the amount of reactants. We know we can use molar ratios to figure out the amount of any substance in the reaction based on the amount of any other substance in the reaction. And we did this in Unit 3. And we've learned that this can be super helpful when it comes to figuring out not only the amount but the concentration of these different solutions. However, not all acids and bases perform in this predictable manner. When it comes to acids and bases, some are known as weak and some are known as strong. And so far we've only talked about strong acids and bases. Strong acids and bases fully dissociate into their ions, meaning when we put these in water, there's no hydrochloric acid left, it's all hydrogen ions and chloride ions, or sodium ions and hydroxide ions. There's no initial reactant left. On the other hand, weak acids and bases do not fully dissociate in water. When you put a weak acid or base in water, they still dissociate somewhat into their ions, but some of the original reactant still remains. The reaction actually goes two ways. So some will go into their ions, and some will change back into the original acid or base. Because the substances are constantly dissociating and reforming, it's really hard to predict the moles of product at any given time, since we're not sure how much is in ionic form and how much is actually in the original compound. So if we're going to use balanced equations to make predictions about amounts of acids and bases, those acids and bases must be strong ones, so that we know the equation represents a one-way reaction. Let's look at this example of a weak acid with a strong base. Now, if this were to react predictably, or as if this was a strong acid, it would dissociate into its ions, just like the strong base, to form two water molecules with the spectator ions floating in solution. However, this is a weak acid, so where some of it might dissociate, like the sodium hydroxide does, some of this weak acid will actually end up reforming in solution, which means now there's not enough free hydrogens to form the water molecules as predicted by this reaction. We end up with extra hydroxides in solution. So we can't actually use this balanced chemical equation to predict accurately how much water will be produced. We can't have a true neutralization reaction with a strong base and a weak acid. So for a reaction to take place in water and for it to occur predictably, or in a way that we can predict the amounts of products produced, two things need to be true. The first is that the reactants must be soluble. The reactants must split into their ions so that the ions can react with each other. The second, if it's a neutralization reaction, the reactants must be strong acids and bases. This way we know that all of the reactants become products and we can make predictions about the amounts and concentrations.